Hi, welcome to a hopefully short lecture recording. This is the material to catch us up in the lectures. We fell behind during our third week of class, so this will get us caught up with the end of where we should be on lecture 5. The 4 and 5 lectures are the trickiest ones to get through in the time that I've got. So I think this is probably the worst. We'll fall behind all semester long. This is where we left off in lecture. On Wednesday, we were talking about how sign numbers are represented, and we were talking about how overflow can happen. And at least for this sample program, pretty quickly you'll notice it overflowing from, well, it starts from a short value of 0, it counts up by 1 over and over again. Eventually, it'll get to the biggest value that a signed short can represent. And then when you add to that, it's going to overflow and it'll turn into what looks like the largest negative value that a signed short can represent. And you would get similar kinds of things in a bunch of other situations, like multiplication. Whenever the result ends up being too big to fit in the type where you're going to store it, that would be an example of overflow. So here, I've got an integer and I set it up to about, or I initialize it to about 65,000, and that fits in an integer just fine, but 65,000, or at least that particular number squared, is a little bit too big to fit in an integer. So you'll get a result that isn't mathematically correct. That'd be an example of overflow. You can get overflow when you change type from a wider type to a narrower type. In that bottom example on the slide, that top number, 1,200,000,000 and some million, fits in an integer just fine, but it doesn't fit in a short. So the short value after that assignment wouldn't be correct. You can even get overflow changing signedness. That makes sense. If you ask for an unsigned value, you get more range on the positive side. If you ask for a signed value, you can store some positive and negative numbers. And if you try to assign one of those values that uh, uh, one of those values that's out of the range for the signed or unsigned type, it won't work. Sorry, it might make more sense to talk about some examples. So here I start out a short at -1. That fits just fine in a signed short. But if I assign that to unsigned, that's one of those, it's a negative value, so it can't really represent that. It'll get a copy of the same bits, which for -1, we saw that's just 16 ones in a row for a short, 16 1 bits. But when you assign that to an unsigned short, it won't look like a negative value anymore. It'll look like a really big positive value. The same thing can happen the other way here. An unsigned short can store a value of 40,000, a big-ish positive value, but that's out of the range for a signed short. So when you do that assignment, you'll get the same bit pattern. But here, if 40,000 is represented with this sequence of 16 bits, then that's going to look like a negative number. And that's another example of overflow. You can even get overflow in a special case just for changing the sign of a number. Remember, all of our signed types can store one extra negative value. They got one more values worth of capacity on the negative side. And for int, on the common platform, that value is it, -2,147,000. And that fits just fine as a negative value, but if you try to negate it, it should turn it into a positive value, but it'll be out of range on the positive side. That's that one value that's too big for the positive side, but fits on the negative side. So if you do that assignment at the bottom of that piece of code, you'll get overflow, and the result won't be correct. In particular, it'll overflow, it'll apply the two's complement operation we just talked about. And if you try it out for a value like this, two's complement doesn't work if you run out of bits. You'll get, when you apply the two's complement to that negative value, it gives you back the same value. So negating this 2,147,000,000 and so on value gives you the same value you started with because of overflow. We've been talking about integer types so far. We've left out some of the most tricky types to represent, the top 3 in our table here, floating point types. We already said the C standard doesn't require you to represent signed values or floating point values in a particular way, but there is a standard that's very common for how those should be represented. And that's the same standard used on the common platform. You'll find it on a lot of different systems today. It's what Java is typically using inside. Uh, and it's an IEEE standard for floating point numbers. Before we talk about that, let's talk about, I guess, when you write a program, you might have to put literal floating point values in it, just plain old numbers of a floating point type. And kind of like integers, if you just give a floating point number like that 3.14, it'll assume you mean double unless you say otherwise. So constants that have a fractional part are assumed to be double. You can give them a 3 point, like I do at the top, with just an integer part and a fractional part, or you can give them in scientific notation, like I'm doing a little further down. This 6.022 E23 is a way of giving it in scientific notation. The E can be capitalized or lowercase. Uh, Again, by default, those are assumed to be double, but you can put a little suffix on them. If you put an F at the end of a number, you're telling the compiler, even though I didn't put this in a variable, it's just a number, I want you to represent it as a plain old float. Or if you put an L at the end, it'll represent it as long double. Uh, for the for storing the, I've got a comment at the bottom of the slide. Does the type of just a number matter? And it does matter it matters a little bit for writing your program. When the compiler writes out code, if you say, I want this as a long double constant, it's going to take a little more space in your program. But it's also going to be more precise if you ask to represent a value that the language can't represent exactly. You're going to be able to get closer to that value with more bits, with a long double compared to a smaller type like a float. If depending upon how you use that value, the value you choose to represent may require the compiler to convert it to some other type before you have to use it. So if you're using a floating point value, it may be worth it to think about the type you want the compiler to start with. For representing these values, like I said, there's a standard. IEEE is a professional organization of electrical engineers, and they've developed a lot of standards for things in the area of computing. The standard IEEE 754 is the standard that defines how floating point numbers are expected to work, or at least how they can work. And it specifies that floating point numbers are going to be represented internally in scientific notation. You remember scientific notation. That's a way of writing down a number like I've done at the bottom of this slide. Every value has a sign. It's either positive or negative. Every value has a mantissa, representing sort of the precision of the value. And every value has an exponent representing sort of the magnitude, the size of the value. And if you look internally in memory, that's how floating point numbers are stored. So if you've got a float on the common platform, that's 32 bits. Those bits will be divided up like this picture shows. They'll use one bit to say whether the number is positive or negative. So backing up, that's like this plus out front. So there's a sign bit to say whether you're storing a positive or a negative number. There's an exponent that stores how the magnitude of the number, like we said, and that ranges between 8 and 15 bits depending on the floating point type. And there's a mantissa between 23 and 64 bits, again depending on a type. C has 3 different sizes of floating point types, so the ranges I'm giving there reflect the different types you might use. We're going to talk about the single precision floating point type. And then the rest of them are similar. They just use more bits, and they divide up those bits a little bit differently. Single precision floating point type is the same type we get when we use float on the common platform. So that's kind of the smallest, least precise floating point type. And you can kind of see that's where the name double comes from. If a float is single precision and it uses 4 bytes, 32 bits. A double uses twice as much memory, and the format used for that is called double precision floating point. So we'll mostly be talking about the smallest, maybe the simplest one, single precision. So for that representation, how are these bits used? Well, the sign bit is probably the easiest one to think about. It's just 0 or 1 for positive or negative. So if the value is positive, it'll be a 0. If the value is negative, that bit will be a 1. So it just indicates the sign of the value. And we never need more than one of those bits for a particular value. So float uses 1 bit, double uses a lot more memory, but it only needs 1 sign bit, and long double still only needs 1 sign bit. So we have to store those 3 parts: the sign bit, we've taken care of that, the mantissa, and the exponent. For the mantissa, if you rewind a couple of slides, you'll see I wrote it down in base 10 here, the way we normally write a floating point number. But in computing, the mantissa is really going to be stored in binary. So I switched it here to writing it down as a bunch of ones and zeros to show how we're going to store that part of the floating point number as a binary number. We haven't talked about how to do fractions in binary. We talked about how to store integers. How do you store a fractional part in binary? The good thing is it's really the same idea as base 10. Base 10, we spent a little bit of time talking about how it works as a positional number system. And we haven't used it yet, but if you go to the right of the decimal place, you get the same behavior with larger negative powers of your base. So in a base 10 number, if this 3 is the ones place, this next digit to the right of the decimal is the 1/10ths place, and then the 100ths, that's 10 to the -2, the 1,000ths place, that's 10 to the -3. Binary uses the same trick. So in a number with a binary fraction, if this is the ones place, when I move to the right of the point, I get a bit that's worth 1/2. 2 to the -1. And then this next bit would be worth 1/4, 2 to the -2, 1/8, 1/16, 1/32. So if I gave you a number in binary with a fractional part, converting it to base 10, a decimal fraction, would be a similar process to what we did for integers. You would just take the value of each bit, and that's kind of what I've done here. If this bit is worth 1/2, that's in decimal 0.5. This bit's a 0, but it'd be worth 1/4 if it was non-zero. This would be worth 1/8. This is worth 1/16, so I wrote that down, and in decimal that's 0.0625, and this is worth 1/32. In decimal that's 0.03125, and if I add all of those up, the value of each of the 1 bits, I can see that this binary fraction is worth 0.59325. So that was converting from a binary fraction to decimal. What if we wanted to go the other way? Well, here we can use a trick similar to our reduction of powers technique. We talked about 2 techniques for converting base 10 numbers to binary, and the first one of those that we did was the one we called reduction of powers. We started with the high order end and sort of set each bit to 1 as long as it didn't exceed the value we were trying to convert. And we can do the same thing to convert even on the fractional side of the point. So here I've got a base 10 number, 0.34375. Let's say I want to convert that to a binary fraction. I know that this highest order bit, the one, just to the right of the point, is worth 0.5. So if I set that to 1, I would already be too big. That'd be bigger than the number I'm trying to convert. So that highest order bit, or the first bit to the right of the point, must be a 0. The next bit's worth 0.25, so I can set that to 1, and I haven't exceeded that number, 0.34375. And kind of like we saw in on the integer side, if I don't set this to 1, the rest of these bits all together aren't going to add up to enough to hit this number. So I have to set this bit to 1. So I'll set it to 1. I'm trying to come up with a bunch of bits that add up to this number, 0.34375, and I just took care of 0.25 worth of that. So I'll subtract that off, and then the remaining bits have to add up to whatever's left. 0.09375. The next bit, if it was 1, it would be worth 0.125. Well, this is smaller than that, so that next bit better be a 0. Otherwise, these bits would add up to more than what's left in this value. That next bit better be a 0. The next bit after that would be worth, what are we up to? That's half, that's quarter, that's an eighth. That would be worth 1/16, which is 0.0625 in decimal. And that number that I'm trying to add up to is bigger than that. So that next bit better be a 1. If I subtract that off, that leaves me with 0.03125, which is exactly the value of the next bit. Obviously, I picked an easy case to do here. That next bit is worth exactly 0.03125. So if I set it to 1, I've got nothing left. Kind of like we saw on the positive side, I could keep going. I could keep adding in additional zeros on the right, and that doesn't change the value I've got. I've come up with a set of bits that add up to the number I started with exactly, and we can tack on as many zeros to the right as we want. One thing to notice is, well, for this example, I picked a value that converted pretty nicely to make this example work out well, but that's not always going to happen. In fact, if you just make up a value in base 10, you're probably, and then you try to convert it to binary, you're probably going to get a repeating fraction in binary. We can see this if we start with, I guess it's the same example we used earlier. If you start with a nice base 10 number like 0.1, if you use this process to convert to binary, or if you use the process we just talked about and converted this to binary, you would get this binary fraction. And I won't read the whole thing, but I think the interesting part is these last 4 bits. I put a line over those to show that those repeat. If you did this conversion, you would get into a process at the end where you just kept getting 1100, 1100, 1100, and as many copies of that as you wanted, showing that if you start with this value 0.1, you can't perfectly convert it to a fixed number of bits. No number of bits is enough. And that's why we kind of probably remind you a few times that some fractions that look like nice round numbers in base 10 can't be exactly represented as binary fractions. And that's why code like the code at the bottom of this slide, or code that we looked at a couple of days ago, gives you maybe unexpected behavior when you work with it in binary. Here, I've got a floating point value x. I'm going to run until that value hits 1. So as long as it's not 1, I'm going to keep running this loop. And every iteration, I add a 10th. But since I can't represent 1/10 exactly as a binary fraction, it means double can't represent that perfectly. If you start with 0 and add in a 10th 10 times, you're not going to ever exactly hit this 1. You'll hit a number that's really, really close to it, but it's not equal to 1, so the loop will keep running. And then once you add a 10th again, you'll go bigger than 1, and then you'll never go back and hit 1 exactly. So this would be an infinite loop. Down here at the bottom, if I change that to an inequality, this loop will terminate. But if you watch its behavior, it'll probably take 1 more iteration than you expected, because even if you add in a 10th 10 times, you're still not quite up to 1. The approximation that gets used for a 10th is almost a 10th, but a little bit less than a 10th. So even after 10 times adding it in, you're still a little bit less than 1. So I guess a takeaway from this is be careful about using floating point numbers as your loop control variable. It's sometimes hard to think about exactly how they're going to behave. And both of these examples would probably be better, at least if I really had to write code like this. It would probably be better if I controlled the loop with an integer variable, and then I can always compute a floating point value from that if I need to. All right, so we know how to represent fractions in binary. So that's what we're going to do with the mantissa. I guess one thing that's worth remembering is, oh, sorry, one more detail first. We've been writing down floating point numbers as powers of 10, but if the mantissa is in binary, it makes a lot more sense to write them down as powers of 2. And that's the next thing we're going to have to keep in mind. For floating point numbers, the exponent isn't a power of 10 internally. It's a power of 2. And that kind of makes sense because if you represent the exponent as a power of 2 and your mantissa is in binary, then raising or lowering the power is equivalent to moving that point left or right. And that's what I'm trying to show at the bottom of this slide. This number times 2 to the 4th is the same as this number times 2 to the 5th, or this number times 2 to the 6th. For each of these examples, I'm changing the magnitude of the mantissa by moving the point left or right, but I'm compensating, I'm making sure it's still the same value by incrementing or decrementing the exponent on the power of 2. Another thing to notice here is it means when you're writing down a number in floating point, well, it looks like there are multiple ways of writing down the same number, at least in scientific notation. This number is the same as this number is the same as this number. I've moved the point, but I compensated by changing the exponent. If we're going to represent floating point numbers, that's probably a bad thing. We'd like them all to be represented the same way. And here I'm showing the same thing, same idea. Moving that point can be compensated for by changing the exponent. So this is going to work a lot better if we just pick a standard representation. And we say for this, we're normalizing the mantissa. You probably did the same thing when you looked at scientific notation in middle school. For the IEEE format, there may be a bunch of equivalent ways of writing down a number in scientific notation, but the one we're actually going to represent is the normalized one, where we move that point, we pick an exponent that puts the point right to the right of the highest order 1. So this picture kind of shows what I'm talking about. We'll choose an exponent so that there's 1 bit to the left of the exponent, 1 non-zero bit. And then that's the one we'll represent. All the ones at the top of this slide are equivalent, but that's the one we're actually going to store. So again, we'll always normalize the mantissa. So there's 1 non-zero bit, a 1 just to the left of the decimal point. And if we do that, we can use one trick that all of these formats use, and that is, well, if that bit is always going to be a 1, we don't really need to store it. We can just, we could save a little bit of memory by not really storing that 1. If it's always going to be 1, let's just pretend it's a 1 and just store the rest of the bits. So you could think of this as getting that bit for free. You don't have to store it, but when you're doing math with floating point numbers, you just automatically assume it's a 1. And that works fine. Again, you could think of that as kind of getting 1 bit of precision for free. A disadvantage of that is, well, it requires you to have a 1 bit, at least a 1 bit somewhere in the mantissa. And not all numbers have that. Specifically, the number 0 is going to give you problems because there's no 1 bit to put just to the left of the decimal point. We're going to fix that. We'll just fix it a couple of slides from now. So for now, we'll assume that we can always normalize the mantissa, and we'll come up with a special way of handling 0. I guess one more trick we have to worry about, and this is probably the simplest, is we said, well, the mantissa, that's going to be stored in binary. So we figured out how to do binary fractions. The exponent, that's really going to be powers of 2 rather than powers of 10. So that was pretty easy. In fact, it works better with the mantissa because it makes it easy to talk about moving the point. The last trick is, well, the exponent itself is going to be stored as a binary number. And that's what I'm showing here. I've been writing it down as things like a 9, but internally, the exponent's going to be stored in binary. And the exponent could be a positive or a negative number or 0. It shows how to shift the decimal point or the point to normalize the mantissa. And you may have to shift it left or right. So you may need a positive or a negative number for that. So for the exponent, we need to store a number in binary that could be positive or negative. We just figured out a good way to do that with 2's complement, but that's not what this system uses. It uses a trick. So for the exponent part of scientific notation, it uses a trick called a biased exponent as a way of handling positive or negative exponents. And at least for an 8-bit exponent, what that means is to store the exponent, if your exponent is 7, let's say, you're not really going to store a 7. You're going to add 127 to that and then store that. That's the bias in the exponent. So for an exponent, instead of just storing it as is, you're going to add a big-ish positive number, and then you're going to store that. And that will handle storing negative exponents, because if you started with a negative exponent, you don't actually have to store that negative value. You're going to add a big positive number to it and store that. So all of your exponents, at least exponents within a particular range, are going to you're going to store them as positive numbers after you've added this bias. So maybe some examples will help show what I'm talking about here. For an 8-bit exponent, the bias is going to be 127. So if you've got an exponent and you're going to store it using 8 bits in this IEEE floating point format, the number you're really going to store is whatever your exponent is plus 127. So if your exponent is 0, you're going to add 127 to it, and then so 0 plus 127 is 127, and then you're going to store that in binary. And positive 127 looks like that in binary. It's a 0 followed by 7 ones. If your exponent is, let's say, 85, you're going to store it by adding 127 and then storing that in binary. And in binary, that would look like that. Here, just remember, we're storing positive or non-negative numbers. So all 8 bits are magnitude bits. That top bit isn't a sign bit. It's just one more magnitude bit. I'm storing this as an unsigned number, but that's because I took whatever my exponent was and I added a big number to it. I added 127 to it and stored that. And this last example shows how that helps. If you had an exponent of negative 38, you're not going to store that. You're going to add 127 to it, and then it's going to be positive. And then you're going to store that. And in binary, it looks like that last example. So I've been saying for an 8-bit exponent, it makes sense to use a binary of a bias of 127. An 8-bit exponent, that's what the single precision, the float type uses. Double, you'll see a slide from now, that uses an 11-bit exponent. So they use a bigger bias, 1023. Long double uses a 15-bit exponent. So they use a bias of around 16,000. We're going to focus on the smallest of these types. We said we'll worry about doing conversion for just the single precision float type. And that uses the smallest capacity for each of these fields. So single precision float is stored in 4 bytes. That's 32 bits. It uses 1 bit for the sign. It uses 23 bits for the mantissa, and the remaining 8 bits for the exponent. So I made a little picture to show how you could think about this. For double, They still only need one sign bit. They spend 11 bits on the exponent. So a little more representation to store larger range, but most of the extra bits go to the mantissa, 52 bits for the mantissa. So a lot more precision for this type. For long double, well, that's 16 bytes on the common platform. And it uses still just 1 bit for the sign bit, 15 bits for the exponent, 64 bits for the mantissa, and it's even got some bits that it doesn't use. Of those 16 bytes, it's leaving, sorry, I'm trying to count up. It's leaving a bunch of bits unused in that space. Down at the bottom, I've given some rules of thumb for how you can think about the range of these types. Float, the one we've been talking about, has a range. It gives you about 7 decimal digits worth of precision. If you've got 23, really 24 bits with the free bit that we don't have to store, that's equivalent to about 7 decimal digits of precision, and a range from about really tiny magnitudes of 10 to the negative 38 up to large magnitudes of 10 to the positive 38. For double precision, you get about 15 digits of precision and much bigger range from around 10 to the negative up to 10 to the positive 300. Long double, even more range and way more, or 4 more decimal digits of precision. So we've learned how to do this representation. We ought to be able to do this conversion ourselves. I thought we'd give it a try. So I started with a decimal floating point number, 3.25. Let's see how that would convert to single precision IEEE floating point format. So first, let's take that 3.25 and convert it to binary. On the integer side, that's easy. The 3 is just 1, 1 in binary. And on the fractional side, 0.25, well, that's exactly the value of the second fractional digit. This is worth a half, and this bit is worth a quarter. So that would be 11.01 in binary. So we're looking for what would go in the mantissa. That's going to end up being our mantissa, but the point wouldn't be here. We would normalize by moving it 1 bit to the left. So if we move it 1 bit to the left, we need to increase the exponent. Moving it to the left is making the number smaller. So we need an exponent that's going to undo that. So this would be equivalent to 1.101 times 2 to the first. Now, we're almost done with the conversion. We can see, well, we can see it's a positive number. So our sign bit's going to be 0. There's going to be the part of the mantissa we store. We're not going to store this top bit. And there's our exponent. So we just have to pack those in. Here's a picture that shows what I just talked about. There's our mantissa, but we're not going to store the 1 bit that's to the left of the point. So I copied these mantissa bits into the mantissa part of our representation. Those are our 23 bits for mantissa. These are the 101 that I took from just to the right of the point. And the rest of these are low order zeros. You could fill in with as many zeros on the right side as you wanted, and it wouldn't change the value. So there's our mantissa, everything except this first one. For the exponent, well, our exponent is 1, but we're going to store a number that's 127 more than that. So 1 plus 127 is 128. We need to store that as an 8-bit binary number, and that's a nice round 8-bit binary number. That's 1 followed by 7 zeros. So that's what goes into the exponent part. And like we already said, the sign bit is going to be a 0. So that's what 3.25 looks like in IEEE single precision floating point format. If you looked at this in memory, you'd probably see it as 4 bytes. It's 32 bits, so that's 4 bytes. If you looked at 4 bytes in memory, depending upon how you looked at it, you'd probably write them down in hex. So that's what I did at the bottom. For this first byte, that's the first 8 bits. So I just counted off 8 bits. That's the sign bit of 0 plus the next 7 bits of the exponent. The exponent's 8 bits, but if you start from the sign bit, and it would in memory start from the sign bit, then that gives you 0, 1, 0, 0. Well, that's the 4 here. And then 0, 0, 0, 0. That's the next 0 here. So that's the first byte, 40 in hexadecimal. The next byte, well, in the first byte, we got everything except this last bit of the exponent. So the next byte's going to start at this 0. And then 101, that's the 5 here in hexadecimal. And then the rest of it's all going to be zeros. So that fills in the remaining 0 in the next byte and the next 2 bytes after that. So again, if you looked at it in memory, you probably wouldn't be looking at a bunch of 1s and 0s. Probably, depending upon your program, that would get shown in hexadecimal. Let's try another example. This one will go a little bit faster because we've just had some practice. What if we started with negative 0.4375 and converted that to single precision IEEE floating point format? Well, we'd probably start by converting. So we'll remember that's a negative number. We'll take 0.4375 and convert that to decimal. And I won't go through that in detail, but if you do that, you should get, or sorry, I said convert that to decimal. I should have said convert it to binary. And if you do that yourself, you should get 0.0111. That's going to be our mantissa, but we're going to move the exponent. So there's just one bit to the left. So the exponent will really look like this when we store it. But because we moved it 2 to the left, we'll use an exponent of -2. For the actual number, you're going to have to put that decimal or that point back where it came from. So for the mantissa, we don't store this first bit, so we store just the 1, 1. So that's what I got in the mantissa there. For the exponent, we started with a -2, but we need to add 127. So we're going to be storing 125 as in the slot for the exponent to represent a -2. We'll store -2 plus 127. So 125 in binary looks like that. So that's what I put in the exponent. And the whole thing was negative, so I put a 1 in the sign bit. And in hexadecimal, that's what that should look like. The first 8 bits up to here look like they're BE. And then continuing from right here, the last bit of the exponent, that's E, and then a bunch of zeros. Before we said we're going to have a problem representing 0. Normalizing the mantissa requires a 1 bit somewhere, just so you can put it to the left of the point. And a 0 doesn't have a 1 bit. So what are we going to do? Well, we'll treat it as a kind of special case. To store 0, we'll store the smallest value we can. We could use a 0 for the sign. Smallest exponent we have would be -127, and when we add 127 to that, that would give us 0. So we would store all zeros in the exponent slot, and the smallest mantissa we could have would be all zeros to the right of the point. So that's what we'll store. So IEEE floating point format uses this particular pattern to represent a 0. And some nice things about this are, well, it is at least the smallest value you could possibly store. So it's as close to 0 as you could store, and it's all zeros. So like any other 0 value in memory, it looks like a bunch of 0 bits. So they treat a 0 like a little bit of a special case. They've got a few other special cases they handle. 0 is a case where you have really the smallest exponent you could possibly have, equivalent to a -127. They use the largest possible exponent to represent some other special case values. So if the exponent value is 128, so that'd be stored in memory, it would look like an 8-bit 255, because it'd be that 128 plus another 127. So they use a particular pattern, a 0 for the sign bit, and all zeros for the exponent. They use that to represent a special value that means positive infinity. If you do something like 1 divided by 0, that's what you'll get as the result. They use a similar thing, except with a negative sign to represent negative infinity, And they've even got a representation for what they call not a number. It's when you do a floating point calculation that couldn't possibly evaluate to anything, like 0 divided by 0. You'll get this special not a number value. That's still the 128 exponent, a sign of 0, and a mantissa that's almost positive infinity, but you got one extra 1 bit on the left. And if you do floating point calculations, you can actually catch it using these special case values. I thought we've done 2 conversions where we go from decimal to IEEE float. Let's try going the other way. So here I just made up an IEEE floating point number, and I started you out in hexadecimal. So a byte with 40, a byte with B8, and then a couple of 0 bytes. If I wanted to know what that was in decimal, well, it'd be easiest to convert it to a bunch of bits first. So that 40B8 looks like this, written down in binary, and with the fields split up so they're easy to see. So from the first bit, we can tell it's a positive number. The exponent, well, it's 1, 0, 0, 0, 0, 0, 0, 1. That's 129. So that's really 127 bigger than the actual exponent. We stored a number that's 127 larger than the exponent. So if we want to know what the exponent is, we take that 129, subtract 127, and that means our exponent was really 2. Over on the mantissa side, well, these are everything except the 1 just to the left of the decimal point. So if we wanted to write down the real mantissa, it'd be that 1, and then the rest would just be copied from here. So 1.0111. So as a floating point number, this must be equivalent to 1.0111 times 2 to the second. Or if I wanted to convert this to base 10, it'd be nice to get rid of that 2 to the second. So that means move the decimal place 2 to the right. So this is really 101.11. And now we're almost done, because that times 2 to the 0, or times no change, times a 1. So that 101 is just 5 in base 10. So I put a 5 to the left of the point. And 0.11, well, that's 0.5 for the first bit, plus 0.25 for the next bit. So those 2 bits are worth 0.75. So this number we started with is equivalent to 5.75. So we talked about IEEE floating point format. We spent most of our time on single precision, the float type on the common platform. Those bigger types use the same tricks, most of the same tricks. They just use larger capacities for things like the exponent and the mantissa. Floating point numbers have much bigger range, but they can still overflow if you ask them to compute a value that's outside that range, that's too big of a magnitude. And that's still called overflow in floating point numbers. Here I made an example. I started with a floating point number, a double of 1. Over and over, I print it out, and then I make it twice as big. And if you run this code, it'll print a big number, and then a number that's even bigger, and then a number that's even bigger. But eventually, it'll exceed the capacity of a float. If you back up a whole bunch of slides, back here, we said a double can't store anything bigger than 10 to about 10 to the 308. And this code will exceed that pretty quickly if you let it run. Floating point numbers can overflow, but they can also do what's called underflow. Overflow is when you compute a value that's too big to represent. Underflow is when you compute a value, or you have to work with a value that's too close to 0, too small in magnitude. Floating point numbers have a largest magnitudes that they can represent, and there's also a limit on the small side. You can see that in the sample code here. I wrote similar code that starts with a 1, and on every iteration, it divides by 2, and then prints out the result. In principle, you should get smaller and smaller values on every iteration, but eventually, you're going to exceed this, or you're going to try to compute a value that's smaller than a double can represent. And in that case, it's going to approximate it with a 0. That'll terminate this loop, if you keep dividing by 2, you should never really hit 0, but this code will, because you will underflow. You will ask it to compute a magnitude that's too small for float to represent. One topic left, and that is a conversion between int and float. In principle, floats have more capacity than int. So it seems like you should always be able to convert from float to int. You could certainly have overflow when you go in the other direction. The rules, so when you go, sorry, I hope I said that right. Let me say it again real fast. You can convert between float and int. In principle, float has more capacity. It can represent larger values, but it also has limited precision. We're going to see the result of that when you convert from float to int, any of the floating point types to the integer types. It takes the integer part of the float and stores that in the int if it can, and it throws away the fractional part. It truncates. So that would mean if you started with a float like 3.14 and converted it to an int, you're going to get a 3. If you started with 3.999, almost a 4, it still does the same thing. It keeps the 3 and discards the fractional part. Since floating point numbers have a much bigger range, you might start with a floating point number where even the integer part doesn't fit in an int. And that's what's going on in the last example. This number is 2 to the 40th. And that's a nice round binary number that's well in the range of a float, but not an int. That's too big of a magnitude. And if you try to do that conversion, you're going to get an overflow. When you go the other way, from an int to a float, the rules are the float will use the closest value it can represent. And that may seem a little bit weird because it seems like a float should always be able to represent an integer value that you started with, but that's not always the case. If you start with a nice round integer value, so here I'm going the other way, like 2 to the 30th, and you convert that to a float, well, you'll get something that looks exactly like 2 to the 30th. But what if you start with a value that's just a little bit bigger? So here, this number is 2 to the 30th plus 1, and the next one is 2 to the 30th minus 1. So these are both really close to a nice round number in binary. If you convert these to int, from int to float, to single precision IEEE floating point format, you'll see that all 3 of these numbers convert to the same thing. In the float, that's the closest value that it has to each of these. And down at the bottom, I'm trying to show the reason. Something like 2 to the 30th is a 1 followed by 30 zeros. This one, 2 to the 30th plus 1, is a 1 followed by 30 zeros, except the last bit's a 1, so it's a little bit bigger. If you try to take, so that's what it would look like as an int in memory. 1, a whole bunch of 0 bits and a 1. If you try to convert that to float, its single precision float doesn't have enough bits in its mantissa to represent all of these bits. So it's going to approximate by using the bits it has, the 23 bits it has, to store as much as it can. So it gets this one for free and then 23 bits, but it doesn't have enough room to store these low order bits. So it's going to round to the closest thing it has, which is going to be, it's going to stop at this 0. So converting this to float, you'll have something that looks like this in the floating point representation. And like I tried to show with the red bits, you don't have enough bits in your mantissa to store all of this. So floating point rounding means that the float type may not be able to store exactly every value an int can store because its mantissa isn't big enough. Double could store this. Double has 53 bits in its mantissa. So if you take an int and convert it to a float, there may be some rounding, but you could always convert an int to a double, but not a long. A long has 64 bits of magnitude, which means some long values might have to get approximated when they convert to a double or a float. Long could always convert to a long double. Remember, that had exactly 64 bits of precision. And I think you can see here some of the reason why. It's a floating point type, that can store every value that any of the integer types can store, plus a bunch of other fractional and really large magnitudes. So you might get overflow. I drew these arrows here where you might get, not really overflow, but you might get rounding when you do the conversion from int to float, or long to float or double. Any of these types converted to long double or int converted to double wouldn't have to do any rounding. And with that, I'm sorry that took a while, but now we're caught up and hopefully will not fall too far behind again. Thanks for your attention. I'll see you in class next week.